Bismillahirrahmanirrahim. Welcome to today's tutorial. Today we are going to talk about engineering materials. Under it we have crystal structure and we also have material science. But we are not dealing with material science now. We are just dealing with this crystal structure. And under the crystal structures, because crystal structure is just about the arrangement of atoms according to their regularity in engineering material. And under it we have different type of crystal structures, like up to 14 crystal structures we have. It's just the basic engineering the one they normally use, that is common. We are dealing with just three, which is the FCC, which is force center cubic, BCC, which is body center cubic, and ACP, which is hexagonal close packed. And then under it we have, like, there are some parameters under it, and we have lattice constant, and we also have number of coordination, and we also have atomic packing factor. Each one have their own, and we also have unit cell. Each lattice factors, each crystal structures have their own parameters like this, and each one has the way they calculate them. And firstly, we are going to calculate for the FCC alone, because from the structure, let's first draw the structure for the FCC so that we can know from there, we can know how to understand the way it is. This is a structure, and each structure now, it has its own atom that is bonded, because in a particle, I mean in materials, no matter how it is, we have different atoms that is bound together to form the particles, to make it a solid form. Now this is the example for the FCC, and the way to calculate it, the lattice constant, the coordination number, the atomic factor, and unit cell. To calculate the unit cell for this one now, this is already a cell on its own, but to calculate it now, we already know that all the face of a box comprises of six faces. Kagane. 6 faces, and each faces comprises of the way they calculate it. Now we have edge. Firstly, we have to calculate the edge, which is the edge is 1, 2, 3, 4, 5, 6, 7, 8. Those are the edge, and we have 8. Then multiply by 1 over 8 will give us 1, right? We also have faces, which is 1, 2, 3, 4, 5. This one is for the first face, and the one behind, which is second face, which is we have 6, which is we have 6 faces over 1 1 over 2 will give us 3. Now, the unit cell for FCC will now be 3 plus 1 give us 4. That's the unit cell for the FCC. Now, we are going on for the coordination number, and the coordination number for it is 12. Coordination number for it is 12. And we also have atomic packing factor. That means we have to do some calculations under it. But before we can do a little calculation for the atomic packing factor and the lattice constant, we have to first find the lattice constant first. The lattice constant the formula was derived. It is through the unit cell, from this unit cell box, and here it is. Let me write it. We have something like this. This is how it was calculated. This is how we are going to calculate it. We already know in our Pythagoras theorem, we already know that the hypotenuse square will give us opposite square plus adjacent square. That's it. And the same thing happened to this one too. This one is radius because half of a circle is diameter, and it is radius square. This one will be radius, this one is radius, and this one is 2 radius. But it's not just one ordinary radius, it is 2 radius. And also the remaining one will be A and A, the remaining side, and we have to square it. Well, let's assume this one is hypotenuse, this one will be adjacent, and this one is opposite. And now let's generate our parameters out. Hypotenuse square equal to opposite square equal to plus adjacent square. Then we substitute the values, which are r plus 2r plus r all squared, which is for the hypotenuse. Then for the radius, and for the opposite, which is a square, and adjacent, which is a square. Then if we calculate all these ones together, it will give us 2r plus 2r, the same thing as 4r. They are all squared. Then this one will also give us 2a squared. It also give us 2a squared. Now we are moving from here. Now this value a is our lattice constants, or we call it lattice parameters. The way we wish to call it. Now from there, now we have to make this a square the subject formula. It should now be a square equal to 4r all squared right? Then from there we have a square equal to, we already know that this square is comprises of 4 square and r square. That means the first square will give us 16 and then r square over 2, right? Then we have a square equal to, we can divide this one by this one to give us 1, to give us 8. Now give us a r square, and we have to make a the subject of the formula. That means we have to do what? Divide. We have to square root both sides to cancel this square. That means if you square root the both sides, it will give us a square root equal to square root 8 r square. Then this one will cancel this. Now give us a equal to square root 8 times square root r square. Still the same thing, the way it is like this. It's also the same thing like this. You can just cancel this square. For this one, it now remains a equal to square root 8 times r. Now we are going on short form, which is the short form for this one. Now they give us something like this. Now be a equal to 2, let's say 4, yes, 4 times 2, then times r, right? Short form for this 4 now, it will come out in here. It now be a equal to 2 square root 2 r times r, or r, all are the same thing. But the square, I mean this root, is only for the 2 alone. Then the remaining will just be times for the r. This is our answer for the lattice constants. As we already know, we got this lattice constant. The value is a equal to 2 square root 2 times r, or we can also write it like this, 2 square root 2 r. All are the same. And then in case, because before we can calculate our atomic packing factor, we have to make use of the volume for the FCC, or the volume for each crystal structure we are told to find. But before we can find the volume of it, we already know that volume means anything raised to power 3. That is the volume. And here now, we have to make it a volume. That means we have to square, we have to cube this a, and anything under it will also be what? Will be cubed. Something like this. No, something like this. Then after that, we break it down, which is 3. We start from the 2 ohm, which is, if you make use of the calculator for it, to give you bracket 2 cube 2 bracket all what? All cube. Give us what? 16 cube, right? If you can't make use of calculator like this, if you can't do it like this, there is a short method to do it too. I've also break it down like that too. If we can get 16 root 2, then it will give us times r cube. This is our volume, which is volume for FCC, which is 4 center cubic. This is it. Or if we can't make it like this, normal, it's a normal mathematical calculation, mathematical expression. If we say, because if we say a cube alternative a cube, then from here which is 2 root 2, then r cube. Firstly, if you cube these two, it will give us 8, right? Then times, if you cube this square root 2, it will give us 2 square root 2, then times r cube. Then it will now give us 2 times 8 times 2, it will now give us 16 times square, then r cube. Check it now, it's still the same thing we get. And then let me recollect, refresh back from in here, because there are some, depend on the way they calculate, there are some mathematical expression whereby there are some people whereby from here, let's start from here. Let me get the question here. A square equals to 4r square root 2. From here now, we can do one mathematical expression. If we can't do it the way I did the first one, you can do it like this. If you want to break this one, because it's just mathematical expression, but we still get the same answer if we are making use of the lattice constant or lattice parameter for it. If you want to just say, okay, from here now, you don't want to break it down, you don't want to split this one down, you just say, okay, square root both sides, because you just remove this square to remove it, to make the 8 subject formula. Now be square root both sides, now give us 4r square root over 2 all squared. From here now, this one will cancel this one, it now remain a equal to, this one we already know that it is for each value, which is like this, 4 square times r square over 2. Then each one have their own what? Square root. It will now be, this one will cancel this one will cancel this. It will now remain a equal to 4r over square root 2. This is it. If you can write it like this, because it depends on the way some lecturers will give a student, and also depend on the way the student also understand it, that will determine whether, okay, you know what he's doing or not. And you can also square this one too, you also get the same answer with the volume of FCC2. All are the same, just depend on the mode of understanding. Now we are moving on to the packing factor, so that after the packing factors, so that the video won't be long, packing factors for it. Then packing factor, or we call it atomic packing factor. Atomic packing factor now, it just depends on the volume, the constant volume over the volume of the crystal structure. The constant volume, we already know the constant volume, the volume of a particle, which is a volume of a sphere, which is volume of sphere over volume of crystal structure. Depend on the type of the crystal structure we are talking about, but you have to add times the unit cell. You calculate APF. This one now is for the FCC because it's only FCC we are doing now. After we're done with the FCC, then we go through to the BCC. That will be in our next video. Now, the FCC, atomic packing factor of FCC equal to the volume of the sphere. The volume of a sphere, it will be 4 over 3 by R cube. That's the volume of a sphere times the unit cell, the one we calculated, that is the 4. The unit cell we calculated in here. That is 4 over the volume of the crystal structure. The crystal structure we are dealing with is FCC, which is the volume of the FCC. That will be 16, the one we calculate in here, which is 16 square root 2 R cube. Here it is. Now we have to break these values down to get our answer. Because the atomic packing factor is just like the way it was arranged, the packing factor, the accumulation of it, the crystal structure for the FCC. Because it's also the standard value for it, which is 0.74. That's it. Fine, because in case maybe we were told to find the atomic packing factor for FCC. Now the FCC now, we move it. Let's move FCC of FCC equal to, we already know that this one and this one, they are tally. We cancel them out. Down remain 4 times, we already know the pi. Pi is 3.14 over 3, 10 times 4, right? Then over 16 square root 2. From here now, equal to, if you said this 4 times this 4, it will give you 16. 16 times 3.14 over 3, then over 16 square root 2. Now let's make use of our calculator. Now calculator says 16 times 3.14 give us what? 50.24 equal to 50.24 over 3 all 16 square root 2. Now if we divide this one divided by 3, it was what? It was 747 approximately, or we can say 75. Then we cancel this one out over 16 square root 2. That means our packing factor now is now 16.75 over 16 square root 2. Then atomic packing factor of FCC equal to, then this 16 divided 16 square root 2. Answer will now be 0.74. That is a constant value for our FCC, atomic packing factor for FCC. In case you might see maybe question that says calculate the atomic packing factor of FCC equal to 0.74. These are the steps to follow. I hope you understand. If you understand it, or if you love the channel, I hope please help us. thumb up.